All right, good morning, everyone. My name is Alan Gates. I'm one of the architects and founders at Hortonworks, and we're going to be talking today about the Stinger work that we are doing in collaboration with many other people in the Hive community. So let me kind of jump right into it here. So first of all, what is Stinger? I get a lot of questions about this, excuse me, especially when we first started talking about it. A lot of people got a little bit confused, thought we were coming out with a new product, yet another SQL engine on Hadoop kind of thing. Just want to be really clear, that's not what Stinger is. Stinger is just an initiative. It's a cool code name. When the engineering team actually started working on this, we were just calling it Hive++, and we were calling what's now Tays MRR, and the marketing guys and the managers came along and said, oh, those aren't nearly cool enough names. You got to have a cool name if you're going to do this. So that's where the Stinger stuff comes from. But Stinger is just an initiative to take Hive and do two things to it. There's two main goals here. One is to improve performance to the point that it's a reasonable tool to use for an ad hoc query engine and to connect to your BI tools, right? So we came out and said that we believed we could improve Hive's performance 100x over what it was in Hive 0.10. And so that's one of the main goals of Stinger, is to drive performance way above and beyond what it is. And the goal there really is that it would be an interactive experience, right? That you could sit there and type a query and it's going to come right back to you, in a few seconds instead of a few minutes like it traditionally has. And the second goal for Stinger is that Hive doesn't support all the SQL that people want, particularly users who are used to connecting their data processing systems to BI tools, Tableau or even Excel or whatever you use for doing your business intelligence, for visualizing your data, all those kinds of things. Hive's SQL to date has been really very simple, focused mostly around ETL use cases. And we hear users over and over again saying, you know what, I want to be able to connect it to these tools. I want it to do things like analytics and windowing functions. I want it to be able to do subqueries. I want it to have real SQL data types. So that's the other thrust here in Stinger, is not just to make it faster, but to make it be the right tool for the kinds of things people want to use it for. So I want to talk through today where we're at, what we've done so far, because with the release of Hive 0.11, we've delivered the first set of some of these features, and what we're working on now and where we hope to go in the future. So here's kind of some mileposts along the way. You make a big announcement like this, you say, hey, we're going to make it go 100x faster, we're going to add all these features. You don't do that overnight. You don't do it in a single release. It takes time. And so we've said, okay, we'll come out in phases. We'll do this bit by bit. And so here's kind of the phases we've been working on. So phase one, which has already been released. It was part of Hive 0.11, which came out in May, I believe it was. So that has some of the base optimizations. It has some nice speedups. I'll show you some benchmarks and performance numbers we got out of that. We've added some analytics functions. I'll talk about that as well. And we've added the org file format. We're now working on phase two, where we'll start integrating Hive with Tays, which means using Yarn and Hadoop 2.0. I'll walk a little bit through that. It also means we're rewriting many of the operators inside to be much more efficient. And then finally, beyond that, there's still lots of work to do. I'm not going to be unemployed at the end of this Hive release. There's still going to be lots and lots of work to do in buffer caching, in putting in a real cost-based optimizer, all these kinds of things. So this is a long roadmap going forward. So let's look at some of what we did in Hive 0.11 for performance. The main thrust in the performance work in Hive 0.11 was just to be more efficient about the MapReduce plans that Hive was producing. So for many queries, Hive was producing MapReduce plans that just honestly weren't the most efficient thing it could do. So, and I give a couple examples here. The first one is, and one I'll talk quite a bit about actually, is doing star joins. So for those of you who don't live and breathe data warehousing kinds of things. A star join is where you have one very large table, a fact table, and you have many dimension tables that you want to join to that. And usually the dimension tables are pretty small. In this case, small enough usually that you can fit them in memory. So an efficient way to do that join is to ship those dimension tables to every node on your cluster, or sorry, every node that's going to participate in the query. And each node then gets a slice of the fact table and does the join of that slice of that fact table against the dimension table, right? That way you avoid a reduce pass. You can do that in the map side. It's very efficient. Hive could do that in the past, before Hive 0.11, but it could generally only do it one table at a time. So you'd have to join one dimension table to a slice of the fact and then have another map-only job to do the next dimension table to the map, and on and on and on. So that you got, if you had, say, 4 dimension tables, instead of having one map-only job, you had 4 of them. That's just not super efficient, right? So that was one of the things that was addressed in Hive 0.11. Not only that, it was changed so that you don't have to give hints to Hive to tell it how to do that. You, as the user, don't have to tell Hive, hey, I think this kind of join will work. The optimizer will just figure it out for you. And it also is smart enough to figure out the case where not all the dimension tables will fit in memory. If you have enough dimension tables, or if your dimensions are large enough, it may not be able to fit them all in a single pass. So it will pack what it can into memory, do a map-only job, then rinse and repeat, right? So it'll do the next pass, fitting again as many tables as it can into memory. So it may have to take multiple passes to do the work, but it will still be more efficient than it was before. There were also a lot of places where Hive just didn't collapse adjacent MapReduce jobs where it could. Say you had a group by followed by an order by, but they happen to be on the same key. So at the end of the group by, you've actually already sorted on that key. There's no need to turn around and do an order by. Prior to Hive 0.11, Hive didn't realize that. It just would do the order by anyway, which, that's just kind of goofy. So those are the kinds of things we took on fixing in Hive 0.11. And here's a sample of, some results of how that looks. So this is running a query from the TPC-DS dataset. That's a set of decision support queries put out by the TPC guys. And we ran this at scale 200, which means the entire data set's 200 gigs, not necessarily the scan input of this particular query, which will probably be a third or a quarter of that. And we ran this on 10 EC2 nodes. So that legend might be a little small. Hopefully you can read it. The big blue bar is Hive 0.10 on text, right? So this is kind of goofy, really. Nobody in their right mind would store their data in text if you're trying to do analytics. But we put this bar on there because this is what everybody does. When you see all those benchmarks out there about our system X is 100 times faster than Hive. Well, one of the ways they do that is they use Hive in text with no partitioning. And of course, they're not using text. They're using their own binary formats, which makes sense. So we put that on there too to show, yeah, this is how bad it is with text. So you see that comes out to 1,500 seconds. The red bar there, the next one over, is if you put it in RC file, which is a much more reasonable thing to do. And the green one is if you put it partitioned RC file. So the green one there kind of represents best you can do in Hive 10. And then the short little purple bar is the same query run in Hive 11. Right? So you're going from 630 seconds to about 40 seconds between Hive 10 and Hive 11 for this query. So let's walk quickly through how we did that. I mean, that's a pretty nice speed up. So what's that look like? This TPC-DS query 27 is a very kind of bread and butter decision support query, which is a lot of why we picked it. We thought it represented a lot of user queries. And what it is a 4-way star join with a fact table and 4 dimension tables, followed by a group by and an order by, and that group by and order by happen to be on the same key. So in the Hive 0.10 world, this was 6 MapReduce jobs, right? 1 for each of the dimension joins, and then 1 for the group by and 1 for the order by. Hence why it took so long, right? Now, in the Hive 0.11 world, it's 1 MapReduce job. All the joins are done in the map phase, all 4 of them. You hash between the mapper and the reducer to do the group by, and since the group by and order by are on the same key, you're already done, right? End of story. Just to show that that's kind of not the only thing we did there. There was some other performance work. We picked another query. This is query 82 from the same data set. This is a fact-to-fact join, so that means you're taking two large tables and joining them. You cannot do this using the broadcast join I was talking about, or the dimension join, where you ship the small table to every node, because both tables are large, neither are going to fit in memory. Instead, in this case, we used a strategy Hive has called a sort merge bucket join, which is where you pre-bucket the data the same way on both tables so that you need only join each bucket. Again, the same thing you see with the red, blue, green, as far as those are the options for Hive 10, and then the purple there is Hive 11. So again, some nice speed up, not quite as phenomenal as the last query, but this came from some improvements in the way sort merge bucket join worked with partitioning, so that it was able to make much better use of the partitions and hence get a much better number. So that's kind of where we were with, or what we've done so far with performance. Let me turn now and talk a little bit about where we want to go with performance, what we're working on now. And I'm not going to go in depth in any of these because all these are covered in other talks here, and I want to make sure you get a chance to really get those in depth, but I want to at least cover a little bit of what we're doing. So the first one is Tays, right? I'm sure you've all heard of this by now. Hopefully you were able to attend Arun's talk yesterday on this. If not, I'm sure it'll be archived and you can watch it in streaming. But the big insight in Tays is that MapReduce isn't the best paradigm for running relational queries, right? I mean, we heard about it in the keynotes this morning. Everybody's excited about Yarn. It opens up that opportunity to do much more than MapReduce on a Hadoop cluster. And for those of us who came from a database background, I remember when I first came to MapReduce, I'm like, okay, this is cool, but this isn't really what I want to write a relational processing engine on top of, right? MapReduce just is not the best paradigm for this. So the goal of Tays is to create the underlying execution system that you want for these relational systems like Hive and Pig. So what's that mean? That means instead of just giving you map and reduce as operators, it gives you a general DAG execution. So you can piece together a graph of operators, and you can control how the data flows between them. It's not necessarily one input, one output like in MapReduce. You're going to have a join operator that might have two or more inputs. It's not necessarily, data doesn't have to move by touching disk or touching HDFS as it does between MapReduce jobs now, right? You could stream data via socket. If your query is going to run a really long time, you might still want to write it to disk because you might want to have some kind of fallback mechanism. But instead of encoding that in the execution system, we want the optimizer of Hive or Pig up above to be able to make that choice, right? So when it's constructing this graph of operators, it can decide, okay, I estimate this query is going to run in about 5 seconds. So I don't care if the query fails, right? I can back up and start all over again if I have to. So I'll choose socket-based communication between the tasks, and then if one of the tasks explodes midway through, you just back up and restart the query, and instead of taking 5 seconds, it takes 10 seconds. That's not disaster. On the other hand, if you start running this query and you look at it and go, I think this query is going to run for 3 hours, you really don't want that to blow up at 2 hours and 59 minutes, right? You've lost a lot of time and compute resources if you do that. That's really bogus. So that's where the optimizer can say, okay, I'm going to pick locations in this and I'm going to checkpoint them to HDFS or maybe the local disk, depending on the performance to restartability trade-offs you want to make. And if it blows up somewhere along the way, I can back up and restart from that point and still finish the query. Maybe instead of in 3 hours, I can finish it in 3.5 hours or something, but I don't have to rerun the entire query. These are the kind of things that we're looking for from Tays. Another piece from Tays is that it provides a standing service for us to run those queries. So right now in Hive or Pig or any of these, or regular MapReduce, you spend 5 to 10 seconds at the beginning of every query just spawning tasks, shipping jars around, all that kind of stuff. if our goal is to hit interactive query times where it's going to be coming back to users in a few seconds, if it's taken 15 seconds to start up, we've already blown ourselves out of the window, right? We're already stuck. So Tays is going to help solve that for us. The orc file work, or optimized RC file, is a rewrite of RC file that's tightly integrated to Hive's type model and has support for nested types and gives much better compression and also supports filter pushdown so that you can start to be very aggressive about deciding which types of data to read and which data not to read based on the where clause that the user has given you in the query. I'll have some numbers here to show you in a bit on some of the performance that's driving for us. And then finally, vectorization is work that we're doing to take advantage of modern processors, right? It was the MonadDB guys, 7 or 8 years ago, published a paper where they said basically, if you stop trying to process one record at a time, if instead you process 1,000 records at a time or something like that, you size that batch of records so that it all fits into your L1 cache so that you don't have cache misses when you're trying to go grab those records. And then you write your code so that there's few or no branches and few or no function calls in there so that you don't have any pipeline stalls, you're not flushing your pipeline at some point. Your ability to drive data through and efficiently use that CPU just goes way, way up. So this is work that's actually going on now, and again, I'll have a few numbers to show, but this is really exciting stuff. So both orc file and vectorization are being covered in a talk by Owen and Jitendra from Hortonworks and Eric Hansen from Microsoft, who's been collaborating with us heavily on that. And they'll be talking about that this afternoon at 4:25, and I encourage you to go. It's some really interesting stuff they're doing. Okay, so I showed you some numbers before of where we'd come along. Here's the same two queries. These are numbers for what we're doing now. Unfortunately, you can't directly compare these to the last slides because the last ones were done on EC2, and after we did those numbers, we went out and bought a cluster, so these are actually on our machines at Hortonworks. So the numbers are going to look a little different. But again, you see the blue bars there is Hive 10. And then you'll see Hive 011 CP, that's community preview. Community preview is what that stands for. Basically, that just means what we're working on right now, but we haven't released just yet. So this is not stock Hive 11. This is Hive 11 with a few more patches put in. And then you'll see that with both RC file and orc file for the performance. So again, you see, and also you see two bars, or two sets of data, scale 200 and scale 1000. So that's measured in gigabytes. So the scale 200 is at 200 gigs, scale 1000 is at a terabyte of data. Unfortunately, I don't have numbers for 010 for a terabyte, but you can get a flavor here for, again, how much we're speeding up over Hive 010 and how much orc file is starting to help us out in some of this stuff by just being more efficient at reading the data and being able to push down some of the filtering down into the storage layer so that we're not even reading data that it turns out we know we're not going to need. Kind of another way to look at this graph is to take those two queries again and look at the speed up over using Hive 010 on text as a base. Then you can see here how they compare against Hive 010 with RC, Hive 11 with RC file, Hive 11 with orc file, and then on the rightmost side on query 82, you see Hive RC on top of Tays. So this is the first kind of integration with the Tays stuff. And on Hive query 27, you actually get to see integration with Tays and the vectorization work. Now, unfortunately, the vectorization is still coming along. It doesn't work on hash joins like query 82 yet. So we can't show a number for that, but this gives you some feel for the kind of speed ups we're seeing. So in the spring, when we went out and made that claim about 100x, speeding up Hive 100x, it's very exciting to actually already be approaching that number in some queries. Now, I want to be very clear, this is some queries. We don't feel like we've hit that goal. We're not going to have hit that goal when we've, when we can find one query somewhere we've sped up 100x. That's not fair. That's cheating, right? But it's still a nice, it'll be a very nice milepost along the way when we feel like we've gotten there for one query. So that's, it's very exciting to be able to look at these numbers. So let me show you one other graph here that I think is very interesting. I talked a little bit about Tays and how it enabled more generic DAGs in your execution. The first step of that Hive is making use of, rather than rewriting Hive to use a full DAG engine, which is frankly a fair amount of work, the first step we said is we would take MapReduce jobs and we'd reorganize them as MapReduce reduce jobs. So in places where you had a line of MapReduce jobs, one following another, we would collapse those into one job where it was one map and then a series of reduces, right? That was a very nice, concise first step that we could use to start to prove out the value of this and test the system and integrate Hive with it without ripping the entire insides out of Hive's planner and reorganizing it, right? So this goes along again with taking those incremental steps to get where we want to go. So here's some numbers from that first integration. This is on query 12, which is yet another query from that TPCDS set. This is, if I remember correctly, this is a join followed by group by followed by an order by, but where they're all three separate MapReduce jobs. Because of the way the keys are set, there's no way Hive can collapse those into a single job like it could with the query 27 that I showed you. So this is 3 MapReduce jobs now collapsed into one. So what's the value of this? Obviously, it saves some latency time here. Another big win for doing collapsing these jobs so that they're submitted as one job is now the scheduler can understand this job as a whole unit, right? This is an important piece of Tays as well, especially when it can do the full DAGs to hand there. Instead of seeing pieces of the job a little at a time, Yarn can now see the entire job you're going to run. It can reason about that, and it can schedule based on your needs for that. It's also important because it means you can't get interrupted in the middle, right? Today, if you're using Hive or Pig or anything like that where you're chaining MapReduce jobs, say you have 2 MapReduce jobs, but you're running on a busy cluster, in Hadoop 1, the job tracker has absolutely no understanding that those 2 jobs are related. So you can run the first job, and then for whatever reason, you get swapped out, and you may wait 5 minutes or 10 minutes or who knows however long until there's slots on the cluster again before your other job goes. This prevents that kind of stuff, right? Now the scheduler can see your work as one integrated unit and operate it on it accordingly. All right, so that was what are we working on now? Then the next question is where do we go from here? What else is there to do? There's lots and lots of stuff to do. One of them is we got to push down the startup time for Hive queries. I've already referenced the fact that there's a lot of startup time in Hadoop, that you're spending time spinning up tasks, shipping jars around, all that kind of stuff, and Tays is going to resolve that for us. But it's always convenient to blame your problems on somebody else, and I always like to tell the MapReduce team how they need to make it faster. But it turns out that there's a fair amount of work that needs to happen in Hive as well. It's actually spending a good another 5, well, depending on the size of the table, a good another 5 to 10 seconds itself getting going. And most of that time is just in interacting with the metadata. It actually turns out it takes a long time for Hive to figure out all the partitions that are in a table and ship that back to to the query planner. So we need to drive that down to near nothing, right? I mean, Hive needs to be able to do the query planning in half a second or something for any reasonable size table. It's just doesn't make any sense that it takes it 5 to 10 seconds to do that. We need to keep working on the optimizer. There's still a lot of work to do there. And there's some exciting work going on actually right now. I guess I should have put this in the working on now category because we have some people from Ohio State working with us and interning with us this summer at Hortonworks, integrating the work they've done called the YSmart optimizer. So this is an optimizer. This is an addition to the optimizer that makes it so it can figure out when parts of your query are correlated and can do those pieces together. So say you have a query that, say you're going to self-join a table, right? Right now, Hive scans that table twice and then does the join inside, which is just silly, right? And that's a very simple example, but there are lots of queries where you end up using, the same query, the same table over again in the query, or maybe you're joining two tables the same way in the query, but it's not immediately obvious to Hive right now that that's what you're doing, and so it ends up doing it twice. This YSmart optimizer works on finding those correlated pieces and combining them so you do them once. And also, we've got to start using statistics like every real database in the world does to start planning our queries, right? We've got to start planning how do we work with MapReduce? What's the right number of mappers and reducers? Or moving into the Tays world, what's the right number of, what's the right parallelism for each task out there? When you've got two possible plans to execute something, I could implement the join this way or this way, which am I going to choose? We need to start using cost-based optimizer type algorithms to do that. And Hive now has the statistics it needs to do that. The next piece is just to put in the optimizer to start to make those decisions. And then finally, on this front, we've got to figure out how to do buffer caching, and this is something we got to work with the HDFS team on, right? Today, there isn't really a lot of buffer caching in HDFS. You're reading straight from disk every time, and often you'll find that there are hot data sets that it makes sense to cache in memory somewhere, and you'd like to be able to make use of that to really speed up your queries. So that's another area that we need to invest in. All right, so I've talked a lot about performance. Let me kind of switch direction here and talk a little bit about the extending SQL that I said was also another leg of Stinger. So what did we do in Hive 011? There's kind of two main things that we started in Hive 011 that we think are pretty big additions to Hive and we're pretty excited about. One is adding a decimal type. So this is fixed precision calculation. If you want to work with currency or other things where the fact that 1.99 times 1 might equal 1.989999 isn't okay, this is what you want, right? This is for those kind of calculations. And then the other is the addition of windowing and analytics functions. This is something we actually heard from a lot of users that they wanted to be able to do in Hive. It's a very common thing to do in analytics or decision support type queries. So this work was actually done by engineers at SAP. This is one of those great things about open source where you go, your customers come to you and say, we really need your product to do this, and about the same time somebody pops up from another company and says, look, I just built that. And you go, yay, right? This was added in Hive 011. It adds pretty much all the standard analytics and windowing functions, rank, lead, lag, row number, NTILE, all those kinds of things. So you can now put those in an over clause and use those in your SQL. All right, so what are we doing? What are we working on now for SQL extensions? What do we kind of see as the next thing? So here's the areas that we're hearing people talk about that they want to see improvements in Hive, and kind of what are blocking them from what they want to do. One of the big ones we hear is subqueries. People want to be able to write subqueries. Now, Hive does support subqueries in the from clause, but it doesn't support them in the where clause. So if you want to say where in and then give some subquery, that doesn't work today. So we're actively working on that. We want to add support for that in clause in the where first, and we obviously, just because it's easiest, we want to start with doing non-correlated subqueries. So that means where the subquery can be evaluated once before the main query and then used in evaluating the main query. A correlated subquery is where there's something in the subquery that requires it to be reevaluated on every row of the outer query. That's a harder problem to solve. It is solvable, but it's, that's more work, so that's not going to be in the first pass. The next one we see a fair amount of is data type conformance, right? Hive has basically a Java type model. It was built by people who are very comfortable with Java, who were using it very close to other Java type things, so it thinks about ints and strings and floats mostly, which for where it started and the fact that it was used a lot with MapReduce was a great place to start. But as Hadoop becomes more mainstream, as more and more people are connecting this to existing data systems, this doesn't work real well, right? If you try to take Hive and connect it to your data warehousing system, to your relational database, they don't think in strings, right? They think in chars and varchars. They think in dates. They think in all these types that Hive doesn't support yet. So that's a major area of push here. And you kind of see the first part of that in the addition of the decimal type in Hive 0.11, but we want to keep investing in that and get the date type in, get char and varchar so that we have bounded strings, start allowing users to specify precision and scale for things like decimal and float, because this is important when connecting it to your relational systems as well, right? Because if they're going to say, oh, this is a decimal, they want to be able to talk about, I know it's decimal of scale 5 precision 5 and scale 2. Hive right now just says, oh, it's just a decimal, right? So, though actually Hive does have a default value, and if you knew it, you could program to it, but it's not necessarily something that's easy to see or understand. So we want to start adding all that. And then finally, Hive's security model is very immature at this point. It was really built early on just to avoid, certainly not to avoid maliciousness, just to avoid stupidity, and even it only avoids pretty extreme forms of stupidity, frankly. Even minor stupidity is still pretty vulnerable to it. So, it's still pretty vulnerable too. So we want to start fixing that kind of stuff, right? That's just something we know is going to be required for enterprise adoption of this. All right, let's see. And with that, that kind of concludes my, the overview of where we've been, where we're going. I think there's a couple mics up here. If you guys have questions, I'm happy to take them.
What's the approximate timeline for these improvements? Do you have a sense for when some of these are going to come to fruition?
Well, so the things that I talked about that we're kind of working on now, we hope to have stuff out by the fall, right? So I can say that. For the things that are in the what's beyond that, I don't have a roadmap. I mean, I have a roadmap in terms of those are the things we want to work on, but I don't have plans as far as we'll release it this and this and this. Like I said, this is going to be an ongoing thing, so you will see significant increases in performance and functionality every 3 to 4 months for a while now. Yes?
When you move to a query optimizer, it's nice to have insight into those stats and visualizations, like a query plan that sees the rest. Any plans?
Yes, there is. So yeah, thank you. That's a good question. So Hive does have an explained plan right now, but you kind of have to be deep in the art of Hive to actually understand that. So one thing we would like to do is make that actually usable and readable by others. And if I remember correctly, I saw something, not from Hortonworks, but somebody else in the community already had some thoughts on how to do that and how to expand that. So, but we agree and know it's definitely something we need to work on.
Hi, obviously this is very exciting. For the EC2 instances, what type of EC2 instance was used? Is it compute optimized or memory optimized?
I don't remember off the top of my head. I would have to go back and look and tell you. It's been months since we ran them, and I don't remember what we used. Sorry.
Thank you.
Any plans to add the time and timestamp and the time zone?
So yes. When, I'm not sure. So timestamps are actually already there. It doesn't support any time zone, but you can give a particular timestamp down to millisecond or nanosecond, I don't remember, precision. But we definitely, when we looked at what to do with the date types, at first we said, okay, we can do all the dates, up to interval and time zone and everything, and then we said, okay, what steps can we take in that? And it looked like just straight date was the best first step, and then after that, we'll keep evaluating where to go next.
For dealing with the temporal data, timestamp is critical, and thereby interval.
Agreed. I mean, we don't have any debate, it's just how fast can we get there, all right?
Just want you to add to the list.
Sure, no, always happy to take requirements. Other questions? All right, well, thank you very much.